Hey everyone, I want to welcome Graham Neubig. Graham Neubig is associate professor at the language, is associate professor at the Language Technologies Institute of Carnegie Mellon, and the current CEO of a company called Inspired Cognition. His research focuses on natural language processing with a focus on multilingual NLP, natural language interface to computers, and machine learning methods for NLP systems, building and evaluation. His final goal is that every person in the world should be able to communicate with each other and with computers. He also contributes to making NLP research more accessible through open publishing of research papers, like advanced NLP course materials and video lectures and open source software. And all of these are available on his website. So now I'll let you take it away. Yeah.
Okay. Thank you. So hi everyone. I'm happy to give a talk here. It's very nice to be here. It's my first time coming to the Strata Center, so I was very excited to look at all the architecture. So this time I'm going to be talking about explaining to learn and learning to explain. And the basic idea is I'm talking about model interpretability for machine learning models. And when we talk about interpretability, what do we mean by interpretability? These are just some example definitions that people have given before in the literature. So for example, by explaining a prediction, we mean presenting textual or visual artifacts that provide qualitative understanding of relationships between an instance's components, words, text, patches, and images in the model's prediction. That's a narrow definition, but it's one definition of how you could do it in explainability. The GDPR, which is kind of the law of the land in Europe, says you need to offer meaningful information about the logic behind automated decisions. Another way you could define it is a form of interpretability and image processing. This looks like that agrees with the way humans describe their own thinking and classification tasks. So basically, you should be describing something that's similar to what humans are thinking. So actually, all of these are pretty different, right? Like they're not super in concert, and you can think of ways where one would be true, but the other would not be true, for example. So I'll just mention that. The second question is interpretability. Why do we want to have interpretable systems? I think we can make a lot of intuitive arguments, but here are some arguments that people have made. The first one is that we want to understand models. Sure, that's good, but it's a little bit vague. More concretely, we might want to engender trust in the system. So we might want people to be able to trust the outputs of a system. We might also want to justify predictions to stakeholders. So if somebody got denied a loan, you might want to explain why they were denied a loan, for example. And in fact, according to GDPR, that might even be a legal requirement. Also to debug models. So our model isn't working as expected. How can we go in and fix it? Offering recourse. So if somebody was wronged by a model, they're open to legal liability. Assessing robustness. Is your model going to work on a new distribution or not? That's something you'd kind of like to know. Identifying causal factors, ensuring fairness, make sure it's not discriminating against people, complying with regulations, et cetera, et cetera. So we have all kinds of different reasons why we might want to be doing interpretability. The problem with all of these reasons is they're all really fuzzy and abstract, right? So it's not super easy to say, okay, we came up with this new interpretability method. Does it, compared to some other interpretability method we created, is it helping users identify causal factors better? How would you do that in a controlled experimental setting? Or is it helping us comply with regulations better? Sure, one way you could do it is you could deploy it and see if anybody sues you for a GDPR violation, but that's probably not an ideal way of assessing your explanation, right? So yeah, it's difficult is what I want to say. This talk, I'm going to focus mainly on interpretability for model understanding. And I'm going to take the kind of fuzzy approach of just saying we want to understand models better, as opposed to saying we want to like trust them more or justify predictions better or something like this. And so from this point of view, I'm going to say interpretation of a model or its output is any insight that measurably improves the user's understanding of the model. With respect to this, you need to think about who is the audience, what type of understanding they'd be forming, and how we would measure it. As a test bed here for this, I'm going to talk about explanation through saliency maps. Is a specific type of explanation. This is a subset of all the explanations you could be doing, but it's one that's relatively easy to implement and measure. And so, like, let's say we have some questions like, why is this email marked spam or important, or why am I seeing this ad? We would basically show people some relevant factors that go into making this decision. And there's a bunch of papers on how to do this. There's this survey here on, interpretability and learning. Why should I trust my classifier? And, like tons and tons and tons. You take a screenshot of all of them and you get all of them here. We have hundreds of methods for explanations, identifying salient input portions. Just to give a few examples of them, one very famous one, probably because it's one of the first ones, is this method called LIME. Basically, the way it works is you take your current input example. And so let's say the plus here is our current input example. And we do minor perturbations to this input example, like we change one word, or we change two words, or we change certain pixels or something like this. We take this like local neighborhood of our input examples, and then we run a classifier over it, train a classifier, and use the weights of that classifier to explain our model. So that's, just one way of doing explanations. And it gives us outputs that look a little bit like this. And like, it's hard to believe that a movie this bad could actually be released, And this is a negative review, but if you perturb certain parts of this input, the review is classified as like less negative than it was before. So these are kind of viewed as the important parts, and similarly for images. LIME uses a linear model, but there's other things you could do. You could use other models like decision trees or nearest neighbors or finite state machines. It doesn't really matter that it's a linear model. It just matters that you're perturbing the inputs and training a surrogate model on it. Another example is sensitivity or gradient-based methods. And basically, these are various methods that calculate all the way through a neural network. And then after you've calculated all the way through the neural network, you do backprop back into the inputs. And then you use the gradients on the inputs to somehow identify which parts of the inputs are supposedly important. The very simplest example of this, let's see if you can see my mouse. Well, the very simplest example of this is the one on the top, where you basically calculate the gradient with respect to each input that you're interested in, like a word embedding or something like this. You multiply the input by this gradient, and that gives you the supposed importance of this input. And then there's a whole bunch of other ones like integrated gradients and others. It's not really important as long as you know the general idea here. And so here are some examples of what this looks like. I showed you some pictures of what LIME looks like. I showed you some pictures of what integrated gradients looks like. And now the question is, which one do you want to use in your next system that you're deploying, or which one do you want to use for your next experiment to be using? Or even if we just look at this individual slide, here's an example from gradients times input and an example from integrated gradients. Which one kind of looks better? Maybe the one on the left. Anyone thinks integrated gradients looks better? Yeah. What about gradients at image? I guess no. So integrated gradients wins, and I'm in the lucky situation of having lots of MIT PhD students or students sitting in the room for me. So I can just ask you, and then you tell me which one you like better. And now I guess I'll be using integrated gradients. But actually, it's not that simple. Here we have GradCam. We have all of these other examples, but like one thing is I just showed you one picture of a camera, and now I'm showing you one picture of an 8. And it's not really like a systematic understanding of how well these models are going to do on a big data set or any other thing like that. And so if we think about how a lot of previous work has evaluated these, Very often it's qualitative. It's like I show you a bunch of pretty pictures and you say, yes, your picture looks prettier than the previous picture. And now, like model explanation is good. And the funny thing is that, a very large number of papers have been published precisely this way, and we don't have a really good quantitative understanding of which one is better. Let me show you another example. So here we have two explanation methods explaining a model, method 1 and method 2. Which one do you think is a better explanation of the model's reasoning about this negative sentiment prediction? I'll let you read it for a little bit. Who thinks method 1 is better? Okay, who thinks method 2 is better? Okay, so that's a good question. And this is actually a trick question because these are the same explanation method for two different models. And so if you don't know what the underlying model is, you can't decide which explanation method is better. These are both Lime, it's just for two different prediction models. And different prediction models are, paying attention to different things when they make their predictions. So because of that, it's actually model dependent as well. Final thing before I stop like complaining is there's also little agreement among explanation techniques. So we'll have different explanation techniques that make different explanations, and actually their overlap on very long sentences. This is the top 10% of tokens on very, very long documents, and actually the overlap is not very good. Yeah.
What task is this for?
This particular task, if I remember correctly, is for sentiment classification over documents, over longer reviews. Yeah. So one common way, which I think is marginally better than some of the other methods that people use, is called erasure. And basically what they do in erasure is they remove certain parts of the input according to the explanation method. And then they try to see how much your model accuracy will go down. And then they try to show two things. They erase parts of the input where the explanation method thought it was important, and they see how much the accuracy goes down. And that's the comprehensiveness. And then the sufficiency is they erase the other parts that the model thought wasn't important and see how well you can do. And then they see how much it goes down. And if it basically says, is this a necessary and sufficient explanation for the model getting it correct? So this is good, but on the other hand, what it's doing is it's like blanking out part of the sentence, which is very different than the actual input that the model got. So from the other point of view, that's a little bit weird. So we have a few issues: qualitativeness, and like evaluating on the outside of the support set. Actually, sorry, I moved the slide about the second point until a little bit later, so I'll get to that in a second. But basically, what I want to say is this is not the best state of affairs for evaluating interpretability methods. So we came up with a way of evaluating them called I called it explaining to learn. The actual paper is evaluating explanations. How much do explanations from the teacher aid students? And before I go into the actual method, one possible criterion that you could come up with if you're able to do human experiments is, do explanations help users predict model output? So you show the user an explanation of the model's output, and you say, what do you think the model output is? And here's an example. So we have this person, and this is an age prediction task. So how old do you think the model predicted this guy is based on this explanation? Any ideas? Yeah. 55, okay. 69. Yeah. 30, okay. Well, I guess it's not even very good from that point of view. The actual answer is 77. But you could probably also come up with a better explanation that makes it easier for you to predict what the model thought this guy was, how old this guy was, this one. So this would be a better explanation, right? So if you're showing users explanations at test time, like the best explanation that would allow people to, guess the model prediction is the model prediction itself. So that kind of rules out anything where in this paradigm because it's too easily gameable. So our alternative to this is something we're calling teacher-student evaluation. And the basic idea is that we have a black box model or process, like an AI model, machine learning model of any variety. We have some FX pairs. We show these outputs to the students. So notice these aren't XY pairs. XY pairs would be the input and the true output. We're rather showing the input and the model predicted output because we want to be simulating, we want to be understanding a model, not the true answer. And then at the test phase, we have these students who observe some model outputs, predict what the model would do on new examples, basically. And so here we can't, because we're not getting explanations with the new examples, this makes it impossible to game. You can't just show like 77. You can't just show the model prediction as an explanation because they don't get explanations at test time. And so this is our control group. And then our treatment group is basically, they get exactly the same thing, but in addition to getting the model inputs and outputs, they also get explanations for why the model made this choice. And so the thing that we're arguing is essentially like, if we're able to teach people effectively, that's a good explanation of the model behavior. So more formally, we measure this using simulation accuracy. So we teach the students to approximate the teacher. We show them new examples, and we measure how accurate they are on simulating the teacher here. Any questions so far? Okay, cool. So basically, we aren't the first to propose this. Actually, I realized we should have a reference on our slide, but Hayes and Bunsell proposed a framework where basically you do this with human subjects and you show them a bunch of explanations and then they try to make predictions. The problem with this is several-fold. Number one, you need to have human subjects who understand what a machine learning model is well enough to be able to wrap their head around the idea of simulating a machine learning model. And I'm not sure if you could do this with like a random mechanical Turker. You can do it with a graduate student in machine learning. The second problem is actually you need to show a pretty large number of examples before people can form a mental model of any variety. And because of this, it's essentially hard to get a significant result showing explanations or not. Like no matter how good your explanations are, or at least with the current state of explanations, it's very hard to get a significant result. So what we propose instead is to make this student a machine learning model itself. And so what we're doing is we're taking a teacher model that already does a reasonably good job at the task, and we're distilling that teacher model into a student model and teaching the student model how to mimic the teacher model. And the idea is if we can do this in a smaller number of examples with explanations and without explanations, and essentially our explanations are an effective way of making this process more efficient. Yeah.
So in the prior set of solutions, you're providing the explanations as a tree that only has the not reference.
Exactly. Yeah. Great. So then there's a couple of questions about what you should do here. One is what constitutes an explanation for your task, ET? For the teacher model, how do you generate ET? How do you generate the explanation? And for the student model, how do you incorporate the explanation into the learning process? so that you can improve accuracy. So I'll go through these one by one. We experimented with two different varieties of task. One variety is text classification. Another variety is question answering. And for text classification, we basically just did highlights of the parts of the text that some saliency map method thought was important. So that's an explanation for the task here. And for question answering, similarly, we had highlights of the inputs based on like the inputs and the outputs and other varieties of information that whatever method we're using, we're showing. We also did machine translation. So machine translation also similarly was highlights over the source sentence when we were predicting an individual target word. So we did predictions over individual target words here. With regards to how to generate explanations, we didn't innovate here because we intentionally didn't want to add yet another explanation method to the pool of already many explanation methods. So we essentially used standard methods for this, including LIME, which I talked about before, gradient-based explanations. And also one type of explanation that I neglected to mention at the beginning was attention-based explanations. And attention-based explanations are basically looking into the attention mechanism of a attention model and finding the places where attention has a high value. One interesting thing is these aren't theoretically in any way linked to the prediction that's being made, unlike LIME, which is specifically based on where predictions change, or gradients, which are based on the likelihood of the prediction increasing or decreasing. But we evaluated these anyway. We also did two varieties of ways to incorporate explanations into the learning process. The first one is multitask learning. And what multitask learning does is you jointly try to predict the teacher output, predict the output that the teacher generated, and you try to predict the explanations. So you essentially have a classifier that tries to classify whether a word was selected as important or not according to the explanation method. And what that's doing is that's essentially training the representations learned by the model to effectively identify the words that were considered to be important. The second way we tried to incorporate explanations is through attention regularization. And the basic idea of attention regularization is we try to make the attention of the student model be similar to the explanation that you got from the explanation method. So if the explanation is the thing in green here, we'll try to make the yellow attention of the student model be similar to the thing in green.
Question?
Yes.
The question was how many seats. The answer is 107,000. And the explanation is University of Michigan. In what sense is that an explanation of what does University of Michigan explain there?
So that's a good question. I don't know about this particular example, but I am pretty certain that this is an actual example of some explanation method that was used on this text here. From the point of view of explaining models, I think saliency-based models are not ideal also, because there's obviously some things that you can't explain by just highlighting inputs, and question answering is maybe a very good example of a place where that's not sufficient. So basically I agree that this is not a very good explanation here, but that's what we got from the current models that we tested.
Okay.
Great, thanks. Any other questions while I'm taking pause?
Can you hear me?
Yeah, okay.
Okay, I have a question.
Yeah, sure.
Oh, so first, to answer the previous question about this particular example, I think it's because the question is asking about the University of Michigan. And if you identify university, like Michigan Stadium, the yellow one, you identify Michigan Stadium, you identify it. The rest of the information, like the large chunk of words in the middle, doesn't really matter. So, the question is asking about the Michigan and its, then you can locate the number in the end. I guess that's my reasoning about the model explanation.
Mm-hmm.
And I also have a question. We also train the model to predict the actual label, the true label?
We do not intentionally, because we're not trying to make a better predictor. We're trying to understand why a model made a decision.
But if you train the model to predict the true label, the model may have a better understanding of the task. And then you just need to learn above of that, what's the behavior of the model explanation. I don't know if that makes sense.
Yeah, I think it does. I think in general, if you have a better model overall, it might be able to pick up on the ways that models are succeeding or failing. And one way to make a better model overall would be to train it on the task. Another way to make a better model overall would be to use a better pre-trained model of language or something. So that we didn't investigate at all, but I think it's a good point.
Okay, thank you.
Yeah.
Just related to that, like how do you isolate, specifically when you're doing multitask training setup, how do you distinguish between this is just like generically useful as a multitask as an extra objective from this is specifically useful?
So that's a very good question. Should I repeat the questions for Zoom? Yeah.
Yes,
okay.
please.
Yeah, so there was a question, which is how do we distinguish between the fact that the multitask objective is just generically nice to have versus it is actually, focusing on the explanation, or like the explanation being good is important there. And basically the answer is we can compare multiple explanation techniques when we incorporate them into multitask learning. And then if the multitask learning is more effective with a particular explanation technique, then that kind of indicates that that explanation technique is better. So we also have a non-multi. Yeah. Well, we only have a single model that we're trying to simulate, but we have different explanation techniques for that model. And so then we do I'll show you in the results, but we do multitask learning with the labels from all of the explanation techniques, and we see which number improves more by doing multitask learning.
Yeah, I guess what I'm saying is that I could imagine like that it's explanation task is in fact just a totally unrelated isolated task that requires some kind of deep language understanding of that, right? For the sentence.
Yeah, yeah.
Being asked before just makes it better than everything into this task.
Yeah. But still, the difference between the different explanation techniques would be salient, right? Like it might be possible that a better variety of explanation technique would give you much better results. Maybe I'm misunderstanding the question. Okay. Yeah. Okay. So the first thing that we tried is not specifically doing explanation techniques from not specifically doing like various different explanation techniques for actual models, but instead taking human annotations of salience of particular inputs and applying them to as explanations that we use to aid our models. And basically what we're able to find here is, and this kind of actually maybe speaks a little bit to the question here, is even just incorporating human salience judgments, not particularly with respect to like this particular model or anything like this, helps. And in particular, when we incorporate it through attention regularization, that's somewhat more effective than incorporating it through multitask learning. We also corrupted the human explanations by unselecting marked tokens with various noising probabilities. And the simulation accuracy was negatively correlated with noise probability, as we would expect. So basically better explanations of salience of particular words are in fact helping in improving the accuracy here. So we can't just give like random 0, 1 vectors. But moving to the more important thing where we evaluate different techniques, we put in X, FX in explanation triples. We have a BERT teacher model and a BERT student model because BERT is what you did in 2020 when we did this research, I guess. But so we incorporated this through attention regularization. And with attention regularization, interestingly, the Lime explanations were the worst. The integrated gradients explanations were the second worst, and then the attention explanations were the best. So this is an interesting result. Basically, what we're seeing is there's a very salient difference between the attention between the different explanation methods, and in fact, it is improving a lot, and better methods are improving better. And let me see if I can predict your question, but say it anyway. Yeah.
Pretty sure it's a very low complexity question.
Yeah.
But how do you confound the realization and maybe
Yeah, good question. And that's exactly the question I thought you were going to ask. And it's also surprisingly shown in our next result. And our next result, essentially, we're using multitask learning, and multitask learning shouldn't be biased in any way towards attention, right? Attention regularization, it totally makes sense that it would be biased. But we got almost exactly the same result when we incorporated it through multitask learning. And this was surprising to us at first because, attention actually isn't theoretically linked to, explanation at all. And in fact, there's several papers, including one by the same author who wrote this paper here, that basically says you can game attention-based explanations and make attention look nothing like the, the actual inputs that the model is paying attention to. But nonetheless, we got this result here as well. So that was interesting. Also, if you go in and manually inspect the outputs, it kind of makes sense. You look at the outputs and it does seem that attention is picking out more salient words than other methods, but yeah. Another question that we've gotten is, what if you had a different student model? So here you have BERT and you're training BERT as your student model. So isn't that biasing the results somehow? So we take the BERT student model and we replace it with an LSTM, just LSTM trained from scratch model. And as a student model, it's quite a bit worse. Not surprisingly, because it's not pre-trained. But we can see, that it's still, very capable of improving using these explanations. And at the very least, there's still a salient difference between the Lime explanations and the integrated gradients and attention-based explanations. How consistent are the rankings? The rankings are relatively consistent across different student models. They're consistent across the learning procedures and across hyperparameter choice of a student model. So like one of the interesting things here is, you could say a criticism, what if this is very biased towards your particular experimental setup? Maybe it's not a good evaluation method because it would be biased, but it's not zero bias, but at the very least, it seems to be relatively consistent. So that's the first part. I'd be happy to take any questions here or move to the next one. Yeah. That's a good question. I don't have any results from this set of experiments, but we have another set of experiments where we basically tried to make a really bad teacher. And the way we did this was we sub-selected the data where the teacher got it wrong half of the time. So basically we had it right half of the time and wrong half of the time. And with a really bad teacher, we see a bit more improvement from incorporating explanations, I guess, just because there's more headroom. But I don't have the things on the slides right now, so I could try to follow up with that. Yeah.
So for the like we can certainly start the explanation.
Yeah.
Right, so that task is that kind of like how is that kind of characterized to say like
So basically, we took the embedding from each token and tried to predict whether it was highlighted or not. Yeah, it's by binary classification at each token. So BERT outputs a final embedding from the final layer, and we just do binary tagging. Yeah.
So, I mean, you mentioned to Brandon's question that like maybe these salience-based methods are not always the most useful things. And, like,
Yeah.
You know, thinking adversarially, thinking about like gaming this metric, like the best thing to do would be to take the weights of the feature model, have the explanation technique somehow like encode those weights directly in the explanation, and have the like other supervision procedure just with those weights on that happen with your training. And like obviously this is ridiculous and not useful anyway. But
Yeah.
over what range of like other kinds of explanation methods is other kinds of supervision methods would you expect to like be used?
So that's a really good point. And here, every explanation method is only able to provide the same amount of information, right? It's a like 0-1 bit vector of limited length, limited by the number of tokens. So this is a fair comparison. But what if we remove that restriction?
Well,
Yeah.
Yeah. Like, to what extent should we think about doing this style of evaluation for other more expressive kinds of
Yeah.
like general free text?
So there's a really interesting thing on like model probing in the model probing literature, where basically the model probing literature, they were demonstrating that you can like overfit to the task. You train a classifier to, you know, predict some sort of information from the model, but you can essentially like overfit to this task and do a really good job despite the fact that you're not learning. And so one approach that people take there is they do kind of like information theoretic approaches where it's like the minimum description length. You get a certain amount of description length and you need to do as well as you possibly can within that description length. And maybe that's the appropriate thing here, but we didn't try that out. I think you can also make other like restrictions, like it needs to be in natural language, or it needs to be, you're allowed to have these certain things because we know that people actually might be able to use them, whereas sending people floats probably is not appropriate. So there's a lot of interesting discussion in the like in the more philosophical side of explainability research, but particularly as it pertains to this, I think that's my answer, I guess. So I can go on to the second part. And this is a more recent paper from NeurIPS last year called Learning to Scaffold, Optimizing Model Explanations for Teaching. And this is a follow-up paper to the first paper. So actually half of this paper is just explaining the previous paper. But in the previous section, we covered how to evaluate existing metrics with respect to how well they can teach a student. But what if we want to make the, not metric, the evaluation, the explanation technique better? And so the question is then, can we directly learn explainers to optimize simulability and to optimize the performance of the student model? So up until now, we had fixed explanation techniques, but what if we're now allowed to vary the explanation techniques? However, this is difficult. We can't just do like simple gradient descent into our models, because the whole point of the paradigm that I introduced in the previous section is that you're training a model to do this, prediction. And if you're training a model that's, in your optimization procedure, that's hard to optimize. Yeah.
how does this task differ?
So how does it differ from distillation? In distillation, so actually, in the previous section, it was a lot like distillation, right? You know, we're doing two varieties of distillation. One is distilling the teacher model's predictions into the student model. The other one is distilling the explanation model's predictions into the student model, essentially. So particularly in the multitask learning setup. Here, instead, what we're doing is we're trying to learn a latent variable. Another way to put it is the explanation is a latent variable. And we want to learn a latent variable model that is the best for teaching the student model. Or a latent variable predictor that's best for teaching the student model. So it's not straightforward distillation. Yeah. So to go into a little bit more detail of what I mean by that and what exactly we do, we consider the teacher model T that takes in the input X to produce an output. We want to train the other constrained student model to simulate the teacher model well. And so at training time, we have this simulation loss, which is basically the loss of the difference between the student and the teacher model's predictions. And that at test time, we give it new examples and we test how good it is, simulation accuracy, what I talked about before. And we have explanations for the decisions from the teacher. This is kind of repetitive. So we regularize in the multitask learning setup. And the key assumption is that good explanations help the student learn to simulate the teacher well. So now we frame this as an optimization problem. We would like to optimize our explainer so that the simulation accuracy becomes the best after training the student. And so at student learning time, we have the simulation loss, we have the explainer regularizer. Oh, sorry, you can't see I'm so used to using my my mouse on the slides, but we have the simulation loss at the top and the explainer regularizer at the bottom. And then at student evaluation time, we evaluate with respect to the simulation loss. And so what we do is we train the explainer regularizer to do better, to like maximize this simulation loss. And so it's kind of like a cycle. We do the student learning, student evaluation, and then we do feedback into the explainer. We called this scaffold maximizing training because scaffolding is a name from education on the help that a teacher provides to a student to aid learning. So that's where the name comes from. So how do we do this? We assume that we have a parameterized explainer. In particular, we had two parameterized explainers, one for the teacher and another for the student. And the teacher one is just the one that's generating the explanations. The student one is trained jointly with training the student model. So we have E of phi S and E of phi T. And the previous student loss and the optimal S explainer can be written like this. So basically we have the simulability loss, which is our standard loss here. We have the student explanation and the teacher explanation. And we have the regularizer here. And so what we would like to do is we would like to maximize the accuracy of the student parameterized by all of these things. So basically now, instead of assuming that the explanation technique is fixed, we now have put the parameters of the explanation technique specifically in this into this optimization problem. And we have kind of the optimal values there. And the crucial insight is that the optimal phi theta and phi s are actually functions of phi t. And so we can also find the optimal phi t is a bi-level optimization process. And so we have our inner optimization, where our inner optimization we teach, we have the parameters of the student and the student explainer here. And then in our outer optimization, we're essentially optimizing the parameters of the teacher explainer in order to optimize the student simulability downstream. And how can we optimize this? So in the optimization procedure, if the explainers that we have are also differentiable, we can use gradient-based optimization techniques. So we take one inner step with the student in the student explainer model. You can also kind of think of the student and the student explainer model parameters as just all like one set of parameters for the student. So we take a step to minimize the loss of the student with respect to simulation. And then we take an outer step with the T explainer based on a hypothetical update to the student. So what I mean by this is, let's say that we took this optimization step where we optimize the parameters of the student with one step of gradient descent based on our current teacher explainer. And then we can do an optimization of the parameters of the teacher explainer to essentially maximize the final simulation probability. And so this is a standard, sorry, I'm running out of water and throat capacity. It was great talking to everybody today, but I've been talking since 9:30. So this is a very standard technique for meta learning, if you're familiar with meta learning, which is basically you have one gradient step where you optimize the thing that you want to optimize eventually, and then you have another gradient step of your like meta parameters based on what the hypothetical gradient step would have been. And so here you can think of our regular parameters as the parameters of the student model, and the meta parameters as the parameters of the teacher model. So sorry, that's a little bit complicated. I have lots of equations, and a graphical explanation might have been better. But are there any questions about how we do this? Anyway, like the general idea is the most important thing. So in order to make this work, we also need an explanation technique that allows us to parameterize the explanation technique. And so the way we do this is we actually, instead of using like the gradient-based explanations or anything like that, where it's not very trivial to parameterize them, we consider attention-based explanations, specifically in transformer models. And we obtain saliency from the, one way to obtain saliency from transformers is to extract one of the many attention distributions. So for example, if we have a single token in the transformer, like a CLS token or something like this in BERT, if you're familiar with the BERT model, we could take a single attention head or the average of all of the attention heads in the model and use that as our kind of explanation. So that's a way of taking a whole bunch of attention distributions and converting them into a single explanation. And so what we do is we try to come up with a more principled way to extract the explanation, specifically by weighting together different heads. So the way we do this is we have multiple attention heads. So if we have a self-attention or cross-attention from a transformer-based model, for each one, we have tokens from a query aligned together with keys from whatever context we're paying attention to. We take the row-wise mean of these. So essentially we take a mean over all of these query tokens, and then we weight them together with these lambdas. And these learnable lambdas are essentially the things that we learn in our model. And what that's doing is that's saying, okay, this attention head is more important, this attention head is less important. we're going to be focusing more on using these particular attention heads. And so another way to put this is the explainer parameters are these lambdas, and everything else, it's just a small number of parameters. So we did experiments. We trained students and a teacher explainer in 3 different settings. The first one is where we have no explanations whatsoever. So we set the weight of our explanation regularizer to 0. We also had a few static explainers like gradient times input, integrated gradients, attention, over all layers, attention over only the last layer where we just like average everything together. And we also have the learned explainer where the coefficients are trained jointly with the student. Yeah. And independently of the teacher explainer, we always use attention as the student explainer because that's what we can easily parameterize. Okay. So we tried a variety of tasks. We have the IMDB text classification task. And reviews can either be positive or negative. We pre-trained a Electra model as a backbone for both the teacher and student. We vary a number of examples, 500, 1,000, 2,000 examples. And the results of simulation accuracy, again, this is how accurately the model is able to simulate the output, is essentially we are able to do a lot better than if we used attention over all layers or attention over only the last layer. So it's a pretty dramatic difference by allowing the model to learn which attention heads it should be selecting to do this, particularly at smaller amounts. Another interesting thing is, I don't think human plausibility judgments are the best way to evaluate these models for the same reason that I pointed out before, like they're not actually connected to what the model is using. However, if you do look at overlap with what humans thought were important contexts, that is also going up by using our learning framework here. And here are some examples. Our method is at the bottom. And attention, all layers, and integrated gradients are at the top. And basically what you can see is it's giving much sharper explanations for what output you should be focusing on. I'm going to go through quickly because I think I'm actually, sorry, over time. So we also did image classification and the pictures are pretty. And it works better. So yeah, that's all. So we have, I mean, that's the important takeaway. So we also have a software package that allows you to use this. It's reasonably well organized and easy to incorporate in your models. So, yep, that's all I had for today. So yeah, thank you for having me, and I'm happy to answer any questions.
Hi, I have questions. So is it possible for the teacher and the student learn to communicate in that the explanation actually doesn't explain the label, but so you can just say you always pick the first token when your teacher wants to predict yes, and you always pick the second token when the teacher wants to predict no. And you communicate this message to the student.
Yeah, so this is a really good question. And that would be a problem if we were using the paradigm where you're given an explanation at test time. That's like actually one of the very typical ways you could game the system by doing that. But that doesn't work in our setting because you're not given explanations at test time. So you really need to learn what the model is paying attention to.
You're not given the explanation at test time for?
Yeah, so basically, like, it's what I talked about at the very beginning here. So if you're given an explanation at test time, you can kind of generate like the actual answer to the question at test time. But in our case, what we're doing is we have a training phase where you're given explanations, and then a test phase where you're not given explanations. So basically, if you give these trivial explanations, that won't be helpful for you learning to better simulate the model at test time.
But when you train in the second part of your talk, when you train the teacher and the student jointly, wouldn't they learn this communicative behavior?
So one thing I should point out is that they have no way to communicate, I guess, so through explanations. However, one thing that they could do it is potentially say, okay, a teacher model, you learn if there's a comma in the input to predict positive sentiment, and if there's not a comma in the input, predict negative sentiment. That's kind of like a trivial classification rule that's uninteresting. But the thing is, the teacher model is frozen. So we're not allowed to change the teacher model. And so it's not possible to do that sort of manipulation of the teacher model.
Well, I mean, you're, if I'm understanding correctly, the second part of your talk, you're learning the teacher model such that the explanations can help the student.
Sorry, to clarify, we're learning the teacher explainer. And the teacher explainer is only used at training time. And then at test time, we basically throw away the teacher explainer. And we only use the teacher model. So the teacher model is the thing that makes the predictions. The teacher explainer only explains the predictions. And we're not using the teacher explainer at test time.
I guess still, I don't quite understand. I understand the training and test time difference, but when you train but I think you are also in the training phase of the joint training phase of the teacher and the student models.
Right. So we're not training the teacher model. We're training the teacher explainers. So like if you think of the teacher model's parameters as theta, the things that actually affect its predictions, those are frozen. Those are not trained. But we have the phi, which affects how the explainer explains the model. And those are trained at training time. I can also follow up via email or something later if you'd like.
Oh, okay. Thank you.
Cool. Okay. Yeah, I see one more. Yeah. We didn't actually. We didn't, and I suggested we didn't, but as you're working with students, they sometimes do things anyway. So we ended up with a parameterized explainer. I think it was actually marginally easier to optimize that way. So it might have had a positive effect. I think he actually tried both and was finding optimization was easier with the parameterized explainer, but I'm actually not entirely sure why that's the case. So, yeah. Yeah, thanks a lot.
I think we're just going to hang out here for a few minutes, but
Sure.
someone owns this room at 5, so maybe we're going to just talk outside.
Oh, okay. Sounds great.
Yeah. All right, I'm going to open it up. Thank you so much.
Yeah, thank you.